This is Formal Lab 1, Levitating Balloons. For goal, motivation, and context, the goal of this experiment is to explore how electrostatic charging influences the motion of certain objects. In this example, we're using a balloon as the model system. When the balloon is rubbed against materials such as wool or fabric, electrons transfer between the surfaces, and that creates a net electric charge. This charge stores electric potential energy, which later can be released as motion when the balloons are allowed to repel or attract nearby objects. This formal lab connects concepts in electric energy to real-world applications like filters, atmospheric electricity, and more, and it also provides a hands-on way to visualize how small charge transfers can produce larger motion. Our hypothesis, so the research question we were trying to answer, is how does the time that a balloon is charged impact the amount of charge that is transferred to the balloon? And our hypothesis is that the longer a balloon is charged, so the longer we rub the felt on it, the larger the transfer of charges will be. The reasoning is that we will be able to determine this by looking at maximum velocity, maximum distance traveled, and conservation of energy principles. For our key terms, we have electric energy potential, which is the energy that a charged object possesses due to its position in an electric field measured in joules. And this is the equation that we use to find the charges of our balloons later in our calculations. Kinetic energy, the energy an object possesses due to its motion, Ke equals 1/2 mass velocity squared, and that also we use that in our calculations. Potential energy is the energy stored in an object due to its position relative to other objects or due to the configuration of particles, which is Pe equals mgh. We have the force, so an interaction that causes an object to accelerate, decelerate, or remain at rest. Position, velocity, mass, terminal velocity, acceleration. We use all of those things to find our values. And then uncertainty, which is that it just acknowledges limitations of precise measurements. So our procedure, we used two identical balloons. One was fixed in place at a constant position and charged for 10 seconds against a felt cloth before every trial, and it served as a stationary charge object. Balloon 2 was used as the moving test balloon, and we charged it in three different time intervals, 5 seconds, 10 seconds, and 15. And then for each charging duration, balloon 2 was rubbed against the same cloth for the same time, then released from the same starting location along a surface, horizontally directed at the fixed balloon. Each time interval, we did 3 trials to reduce random error, and then after it was released, the distance traveled by balloon 2 was measured using the meter stick. Between each trials, we neutralized both of the balloon's charges by rubbing tinfoil on them. So for tools, we used Tracker to analyze videos and determine the ball's velocity over time, which is what allowed us to find when terminal velocity was reached. We used a phone camera to record the motion of the balloons, a timer to see how long we were charging the balloons for, tinfoil to neutralize all the charges, and we did that for 10 seconds in between each trial, a meter stick which measured the distance between the balloons and also helped us keep track to make sure that for each trial we were starting at the same distance away from balloon 1 and balloon 2. The balloons we used 2 balloons that were similar in size, and those acted as the objects whose charges we were solving for, and the mass for the balloons was 2.56 grams, and then we just used a felt piece to create the charges. For experiment design and error, our variables, so our independent variable, we have charging time of balloon 2, which is the 5 seconds, 10 seconds, and 15 seconds. Our dependent variables, so is the distance balloon 2 travels after being released, facing towards the fixed charge balloon, which is balloon 1. And our controls is materials used to charge the balloon, balloon 1, environmental conditions, so we use the same location, and the same person handling each balloon. So for our potential sources of error, since the balloons were pre-blown up, there could be a slight difference in mass change, which can affect how far balloon 2 travels. Inconsistent charge transfer during rubbing, so friction, pressure, and speed variation. Actual charge may be different than the assumed value, and balloon 1 is not fixed in the same position each trial, so small shifts, which can cause changing in the electric field, which can impact the distance measurement. So here are our models. So we have the energy bar charts up here, and then here's our free body diagram and the system schema. Our predictions. So we had it predicted that the 5 seconds would travel this 5 seconds would have the highest traveling time, while the 15-second charge would not have as much. So we show that here. What are we solving? So these are our equations here at 5 seconds, 10 seconds, and 15 seconds. And then balloon mass, which is 2.56 grams. So we're trying to find the electric charge. And then we need to find uncertainty, which is in here. So these are just our tracker data for position and velocity at 5 seconds. For trial 1, the maximum distance was 0.878 meters. For trial 2, it was 0.841, and for trial 3, it was 0.902. Our maximum velocity for trial 1 was 1.121, for trial 2 was 1.244, and for trial 3 was 1.087. And the average of the distance was 0.874, and the average for velocity was 1.151. Here's the graphs for 10 seconds. The same thing here. So this is the analysis for 10 seconds, and then here's 15. So here are all results. So for the 5-point charges, we have Q1 equals 8.962 times 10 to the negative 8 coulombs, and Q2 is 1.793 times 10 to the negative 7 coulombs. For 10 seconds, we have Q1 equals 1.063 times 10 to the negative 7 coulombs, and charge 2 was 1.063. They're the same. For 10 seconds, they're the same. And for 15, we have Q1 is 1.18 times 10 to the negative 7 coulombs, and charge 2 is 5.901 times 10 to the negative 8 coulombs. So this does not support our initial hypothesis, which stated that the longer we charge the balloons, the farther it would travel. It's important to consider large variations among constant balloons. So like the balloon charge for 10 seconds in each situation, point value charges, and then error bars are exceedingly large, which makes the interpretation of the data more difficult. So our conclusion and limitations and errors. So one limitation or error would be that the balloons were not the exact same size, the rate of charging balloons, the surface area of the balloon charge. So if you rubbed like a small area versus like a larger area, and then interactions with the floor. There was also a draft in the area as well from people walking in and out. So that could have also been a source of error for how far the balloons were able to travel. And that's it.